As I said earlier, feedback systems happens to be one of my favorite lectures in the entire course, because we can think about real world applications and connect the math to applications in this lecture. So let's begin with talking about what feedback is. Right? Feedback is the process of measuring a controlled variable, for example, measuring the temperature of a room, and then using that information to influence the value of the controlled variable. So, for example, if it is too cold, then you might want to increase the temperature of the room. So, you measure it and then you use that information to turn on the heater, for example. Right? So, you're trying to measure first and then influence the value of the control variable. And you can even take this to more exciting applications. For example, a drone. So if you want a drone to fly at a certain height, then you might want to use a sensor to or altimeter to measure the height of the drone and use that value to influence the current height of the drone, right? So for example, if it is going too low, then you might want to increase the height, and if it is going too high, then you might want to adjust uh, to bring the drone down, right? So that's essentially what feedback is: measuring something and then using that information to influence the value of that same control variable. Now, feedback in systems can be majorly classified as arising naturally or introduced on purpose. We will be more focused on the introduced purposefully case, because we are going to try to control that feedback to make things happen in a certain way. But feedback could also arise naturally. So, for example, if you have audio speakers that are feeding back into a microphone during a public address, that's when you hear a very uncomfortable noise, right? That's your commonly experienced distortion. This happens when the feedback is too strong. So, it could happen naturally in this example. And the way this is going to be unstable, right? Because if the feedback is too strong, the system becomes unstable, and then this gives you a loop of that feedback happening, which will make that uncomfortable noise to increase in strength, to increase in amplitude, making it more and more uncomfortable for you to hear it. And the way you control this is by reducing the gain of your microphone, right? So if a microphone is feeding back into an amplifier, it decrease the gain of the amplifier to control that behavior. So move the system from unstable to close to stable behavior there. So that's arising naturally. On the right column here is feedback introduced on purpose, and this could be done to enhance or control some aspect of a system performance. So, for example, we are talking about the height of the drone. That was feedback introduced on purpose to control the height of the drone. Another example could be design an amplifier to compensate for for uncertainties in the frequency response. Whenever you design an amplifier, you would probably want the amplifier to amplify things irrespective of what frequencies they have. So in terms of the if the x-axis is omega and the y-axis is h of omega, or at least absolute of h of omega, the frequency response of this amplifier, ideally you would want this to be flat, right? Because you would want all frequencies to be amplified by the same gain. But if you do not have such a situation happening for some real amplifier, then you can use feedback to correct for those certain uncertainties. For example, if instead of flat, it was doing something like this, you could use feedback to fix that. Find out what frequencies are getting distorted and then adjust the gain, adjust the strength of those frequencies using that feedback information to bring it back up. We will take a look at that in just a bit, but I'm going to leave this as flat so that we see that that's what I meant with that example. Flat frequency response for the amplifier. That's what is desired in most applications of amplifier. Now, a little bit more discussion about feedback. Feedback also commonly used in stabilizing unstable systems. So if a system is unstable, you can use feedback to get it more closer to a stable behavior. Example is controlling the flight of a drone, right? So if it is an unstable drone, you can use sensors to measure and influence the controlled variable. We are going to analyze one such system. We are going to analyze an inverted pendulum that I'm very excited about. The basic tool that we are going to use to analyze linear feedback systems is Laplace transform for continuous time systems, and we use Z transform for discrete time systems. So today what we are going to be doing is this: analyze linear feedback systems using Laplace transform. And we'll be focusing on the inverted pendulum example. Now for stability, the condition for continuous time systems is that all the system poles should be in the left half of the S-plane. If all the poles of your system are in the left half of the S-plane, then the system is stable. If any one of the pole is on the right half, you know that it is going to be an unstable system. And even if they are on the imaginary axis, things are going to be a little bit risky, right? So things are going to be marginally stable if the poles are on the imaginary axis. Not repeated, complex conjugate. If they are repeated poles on the imaginary axis, we know that that is unstable. Okay, let's move on. How do you analyze a system? And for example, we are going to start off with a feedback system like this, the one that is shown over here. You have an input x of t coming in, and we are going through h of s, that's the transfer function of your forward path. So for example, actually I'm going to call h of s my open loop transfer function. Right? Because if there was no feedback, it would be open loop, right? There's no closed loop. If I remove g of s, then I have an open loop. That means I have only this going on straight through. So in that case, y of s divided by x of s would be h of s. That's your open loop transfer function. That's when there is no feedback. However, if there is feedback, and we are calling this feedback transfer function as g of s, so we measure y, feed it back through g of s as a negative feedback, or it could be positive. Right now we are considering negative feedback. And then we subtract r of t from x of t to get e of t. And then that goes again through h of s. So how do you analyze this system? First off, I'm going to write E as x minus r, right? This summer over here, this has negative feedback from r of t. So E error or E can be written as x minus r. So we have written x minus r here. Take Laplace transform on both sides. You get cap E of s equals cap x of s minus cap r of s. That's equation number 1. Next, we know that E is the input, goes through the transfer function h, you get y at the output, which means by just observing those three things, I can write output in s, y of s equals E of s multiplied by h of s. So in time, it would be a convolution between E of t and h of t. In Laplace, it would be a multiplication. So y of s is equal to E of s multiplied by h of s. That gives you equation 2. Then R of S, which is the Laplace transform of R of t, that can be written as y of s, y of t, Laplace transform of y of t multiplied by g of s. So I can actually call this as, we'll do that later. Now, we have got those three equations. From these three equations, what we are going to do is we are going to substitute 2 and 3 in equation 1. And we are going to write y of s divided by h of s as x of s minus y of s multiplied by g of s. This is by simply manipulating the three equations. Now, if we rewrite this, what we are after is the closed loop transfer function, which means we are after y of s divided by x of s with g of s present. It would come out to be this. The closed loop transfer function q of s equals y of s divided by x of s, Laplace transform of the output divided by Laplace transform of the input, as h divided by 1 plus g times h. H of s is the open loop transfer function, also called as the system dynamics. G of s is the feedback dynamics. So I can say that this is system dynamics. And these are feedback dynamics. There is a very easy way to figure this out. So the trick is to think of this as forward divided by 1 plus product. I remember it as this. So forward, you see this? Let me erase this guy, this guy, this guy, this guy. So forward divided by 1 plus product. Product is multiplication of these two guys. So that's your closed loop transfer function. Next, what is open loop transfer function? Open loop transfer function is simply h of s, which is y of s divided by x of s. So h of s is called the open loop transfer function, which is what is y divided by x when g of s is 0, right? When there is no feedback, when the loop is not closed, it is open. So when that means no feedback. So open loop transfer function is h, closed loop transfer function is h divided by 1 plus gh for this particular system. Questions here? Okay. Now some applications of feedback control. I talked about amplifier design, how we wanted the frequency response of an amplifier to be independent of frequency, a flat frequency response, right? We can use feedback to get that done. How? Let's take a look. Compensation for non-constant frequency response. If x of t is the input, y of t is the output, we have an amplifier with frequency response h of omega. I can use feedback through an attenuator of some attenuation constant k, provide that as a negative feedback, and the claim is that this will make the amplifier independent of frequency, the amplifier gain to be independent of frequency. Let us see that. Q, the closed loop transfer function of this amplifier, is going to be y of omega divided by x of omega, or forward divided by 1 plus product. Forward is h of omega, divided by 1 plus product is k times h of omega. Now, if I choose k of h of omega, this guy right here, to dominate, much greater than 1, then what would happen is Q will become simply 1 divided by K. Because if this dominates, I can ignore 1, h of omega gets cancelled out and you get 1 over K. 1 over K is independent of omega, which means my closed loop transfer function became independent of frequency, which means that it became flat because K is a constant. That's the amount of attenuation. Right? So that's how you can use a negative feedback to get a constant frequency response for an amplifier. Second application here is for inverse system, which means that can I use feedback to get the response of 1 over whatever the system response is, right? So for example, if you start off with original system, which is x going into p of s, you get output of y of t. Can you design a system that does inverse like this? 1 divided by p. And we can do that by connecting a negative feedback through p of s in this particular configuration. X of t, negative feedback, you have a constant multiplier k, that's your y of t. You're taking y of t and feeding it back to through p of s to get you that negative feedback amount. For this, what would be the closed loop transfer function? It would be forward k divided by 1 plus product, 1 plus k times p of s. And if I choose kp of s to be dominant factor in the denominator, then that means that kp of s is much greater than 1. In that case, k would get cancelled out and you would get approximately q of s is 1 over p of s. That is how you would design an inverse system. Now the last column here is actually what we are really trying to understand. Can I use feedback, negative feedback, to stabilize an unstable system? So here is, some of these things are in time, some of these things are in S. So some of them are in Laplace domain. So you have h of s, the transfer function of the open loop transfer function. G of s is the feedback dynamics. And we earlier derived that the closed loop transfer function Q of s is h divided by 1 plus g times h. So for the closed loop transfer function, what is the characteristic equation? Which means what are the values of s for which the denominator goes to 0? In other words, where are the poles for this particular feedback system? Well, for that, you would have to find the denominator polynomial, equate it to 0, and find the values of s that make it 0. And if you want to make the system stable, make sure that the real part of these poles is negative. So choose g of s such that the real part of these poles become negative. That's it. That's in a nutshell, that's what we are after. Choose g of s such that real part of these poles for the closed loop transfer function have a negative real part. That's it. And this leads us to our real world example that I want to focus on, the inverted pendulum. Now, while we are talking about the inverted pendulum, I hope that you guys are trying to balance a pen or a pencil on the palm of your hand. When you try to balance a pencil or a pen on the on the palm of your hand, what is going to happen? Well, of course, if you don't do anything, if you just place it vertically, it would topple over, right? So that means that to begin with, this system of inverted pendulum is going to be unstable. So what do you need to do in order to balance that pencil on top of on the palm of your hand? Well, you would have to move the hand itself, right? So you would have to in real time, you would have to measure how the pencil or pen is toppling over, and you would have to move your hand in such a way that you not let that inverted pendulum topple over. So Jacob has put a YouTube link about the same great series on this exact problem. Go ahead. Now, today's discussion is going to be, all right, we have learned about poles, we have learned about feedback, we have learned some math. Let's apply that to an inverted pendulum exercise and see if it helps stabilize this system or not. So the same idea, balancing a pen or a pencil on palm of your hand, can now can be applied to this inverted pendulum. What we have over here is a pendulum on top of a cart, right? This particular cart can move with certain acceleration a of t. L is the length of the pendulum. X of t is the external disturbance in terms of angular acceleration. So essentially that could be the wind blowing, or this could be someone tapping on the inverted pendulum to force it to topple over. So what would and there is g, the acceleration due to gravity, and there is theta of t, a time varying angle, and essentially we want this to be 0, right? We want theta of t to be 0. That means that the pendulum is vertically upright and it is not going to topple over. So the goal here is move the cart. This is our cart. Move the cart such that theta of t is 0 degrees. So we are going to measure theta of t, and depending on that measurement of theta of t, we are going to increase or decrease the acceleration of the cart. And our goal should be to bring that theta of t to 0, right? That's our goal. Now by itself, the inverted pendulum is going to be unstable, clearly, right? So if we are not moving the cart, and if we just leave the inverted pendulum upright, it is going to topple over, right? Even the slightest bit of movement will topple it over, right? A lot of things have to be perfect in order for it to continue staying upright. Not practical, not stable by any means. So we can apply an external acceleration a of t to keep it balanced. So the goal is going to be this. Even if you have external disturbances, somebody pushing it over, some wind, or something or the other that makes it topple over, we are going to measure theta of t. That is our measurement of the control variable, and then we are going to use that measurement value to change the acceleration of the cart such that theta of t goes to 0. That's going to be our goal. So having talked about that, let's take a look at these two things here. Our x of t is the external disturbance. This is somebody pushing on top of the pendulum to make it topple over. A of t is the acceleration of the cart, that is essentially the feedback information, and the feedback information should be derived using theta of t, our angle with respect to the vertical. And theta of t is the actual output, and we want this output, system output, to be 0. So you have external disturbances, and A of t is the feedback going through the system dynamics, which involves the cart, the pendulum, the length of the pendulum, and all that. Those are all system dynamics, how all the connections are being made. And then the output is essentially a time dependent angle of the pendulum with respect to the vertical axis. So open loop system is of course unstable, and this is an open loop system. You notice there is no feedback here. If there is no feedback, then there is an open loop system. There's no loop. And if there is no loop, that essentially means that we are not accelerating the cart using the information of theta of t. We are just arbitrarily, changing the acceleration. We may be not changing the acceleration at all, or we might be accelerating it by some constant. But if a of t is not being derived from theta of t, then this is a open loop system, and it's going to be, of course, be unstable. The pendulum is not going to be upright. Our goal should be to keep theta of t 0. That angle should be 0. And we can do this by applying the appropriate acceleration. So this acceleration cannot be an arbitrary quantity. It has to be an appropriate acceleration, which means measure theta of t, use that through some feedback dynamics, and then adjust your acceleration, right? Only then your goal can be met to make theta of t going to 0. Now the main question is, what should I put in this feedback dynamics so that theta of t can be 0 and we have a stable inverted pendulum? That's our main problem today. All right, let me erase this. All right, let's continue. Stabilizing system using feedback. You see this? Earlier, we just had x and a going into system dynamics, and theta of t was the output. Now, we are measuring theta of t, the angle, and if it's a large deviation, then we have to quickly increase the acceleration to make sure that the pendulum balances, right? So we measure theta of t and use appropriate feedback dynamics to adjust the acceleration of the cart such that the system becomes stable, which means theta of t goes to 0 degrees, right? That's our goal. So first, measure theta of t, process it through the appropriate feedback dynamics, use that to control the acceleration of the cart. And when the feedback is chosen correctly, and that what is correct and what is not correct is the main question here. When the feedback is chosen correctly, the closed loop system can be stable. We still have to figure out a lot of details about this, but there is a way to do this. Now, some of the initial discussion is going to be through some engineering analysis, right? Like trying to balance out the accelerations. The acceleration due to the disturbance, the acceleration due to the acceleration due to gravity, all of those. If you take the system itself and you write the equation to balance out the accelerations for that inverted pendulum, then you get this. L, which is the length of the pendulum, multiplied by the second derivative of theta of t, which is the output, equals g, which is the acceleration due to gravity, times sine of theta of t, plus length of the pendulum multiplied by the external disturbance x of t, minus a of t times cosine theta of t. That is an equation that balances out the accelerations for that pendulum. Now, remember we said we are going to focus on linear feedback systems. So we are going to try to linearize this equation. It is not linear right now. So how can you make linear? Well, this sine term needs to become linear. That cosine term also needs to become linear. So for that, what we are going to do is assume that theta of t is small. That deviation away from the vertical is pretty small. When the angle is pretty small, then the sine of the angle will be linear. So sine x will be equal to x if x is small, right? So sine theta should approximate to theta of t for small theta of t. And cosine should be approximated to 1 for small angles theta of t. So as long as it is linear, I can make that substitution in my original equation here that I obtained when you balance out the accelerations. The linear system equation will now become this. So by just substituting these guys in the original value, original equation. Now you apply the Laplace transform to find system function. When you apply Laplace transform to this differential equation, theta of s, the Laplace transform of the output, can be written into this form. There are two products here. One is the open loop system function, which means only the system dynamics at play, which is 1 divided by L S squared minus G. And the other is Laplace transform of combined inputs. So one is open loop, which means no feedback. So no feedback means what? No, this term is not there, right? All the others are there. That would give you the open loop system function. And the other one is Laplace transform of combined inputs. So this equation theta of S is being derived by taking the Laplace transform of linear system equation. In this zero state versus, oh, we are assuming zero state here. At the beginning we have zero state. So once I write theta of S, our output in Laplace domain as this function, I can use this to find where are the poles and try to note stability from that. Also note that x of t is an input, the external disturbance that we have no control over. So we are not controlling x of t, that's an external disturbance. The only thing that we can control is the acceleration of the cart, a of t. Where are the open loop poles? So if the system does not have any feedback, then you will have to deal with the open loop transfer function. Where are the pole locations for that? Theta of S is written as 1 divided by Ls squared minus G multiplied by the Laplace transform of the combined inputs, Lx minus A. I can write this as some open loop transfer function H multiplied by this Laplace transform of combined inputs. That gives me H of S, which is the open loop transfer function. The denominator of that is simply Ls squared minus G. Equate that to 0. You find two values of S. Where are those two values of S? One is on the right half plane on the real axis. One is on the left half plane on the real axis. The one that is on the left is stable pole. That's good. But one on the right is absolutely unstable, which makes the overall system unstable. This is essentially how you can say that if you do not have any feedback, the inverted pendulum is going to topple over. It is not going to be stable. No feedback, then unstable. Because the open loop poles are unstable. One of them is stable, the other one is unstable, which means the overall system is unstable, right? So open loop poles tell us whether the system is stable or not when there is no feedback involved. Open loop. Questions here? Now we are coming to the interesting part of this lecture, the real core of this lecture. So if x of t is the input, and if I'm multiplying this with some scalar value L, which is essentially the length of the pendulum, going through the open loop transfer function h of s, which we derived earlier as 1 divided by Ls squared minus G, the output is theta of t. I measure theta and I use that through some feedback dynamics G of S to get my acceleration, which is the feedback, right? So the goal here is going to be, if you have a closed loop system as shown, can you choose G of S to make the overall system stable? So choosing G of S is the remaining question. So using the earlier result, what is our closed loop transfer function? It is so closed loop transfer function is this, right? Theta of S divided by x of S. That's our closed loop transfer function. So we are essentially writing this as theta here, x here, but it is still forward divided by 1 plus product. Forward is this multiplied by that. 1 plus product is product. 1 plus product. Product is G multiplied by H. That's an earlier result. So we have got the closed loop transfer function now. That means that I can find out where the closed loop poles lie. But right now I just have g of s. So the first g of s I'm going to consider is a very, very simple g of s. It is proportional feedback, which means accelerate the cart proportional to the angle. So if theta of t is high, accelerate the cart faster. If theta of t is low, acceleration low, right? So proportional feedback essentially means g of s is k1, some constant k1. So theta of t goes in, gets multiplied by k1, and your acceleration is now k1 multiplied by theta of t. If that is the case, your closed loop transfer function will become this. And you will have two pole locations in this case. One is at plus square root of g minus k1 divided by L, and the other is at minus square root of g minus k1 divided by L. Clearly, they are two separate poles, right? And if you think about k1 equals 0, one is going to be on the right half, one is on the left half of the plane. But because k1 influences the location of the poles, we can try to figure out whether we can make this system stable somehow, right? So what we are going to do is we are going to sketch out these two poles, and then we are going to see how these poles move as you change k1. That gives us this. The root locus. The root locus is a sketch that shows us how the poles move in the S-plane. That's it. It's a sketch. So where do we start? Let us start with k1 equals 0. If k1 equals 0, then the two poles are actually the open loop poles, right? Because, so you see this g minus k1 divided by L. So if you make this k1 0, you have plus or minus square root of g divided by L. Those are the two poles, the same as open loop poles that we saw earlier. This guy is stable, but this guy is unstable. So that means that when k1 is 0, we have unstable system. However, what happens when you increase k1 or decrease k1? If you decrease k1, this pole moves to the right, which means more red, more unstable. This pole moves to the left, which is good, right? Stability, that's fine. But it moves left. The problem here, the reason why it is red is because this guy moves to the right, becoming more and more unstable. That's what happens when k1 is less than 0. But if k1 is greater than 0, you see what happens. This pole moves right, this pole moves left. So that's good. This is moving left, that's good. But they meet on the imaginary axis and travel vertically up and down, which means when k1 is greater than 0, we could get marginally stable behavior, which means there will be oscillations, which means our pendulum will be going back and forth, right? But it will still stay upright. It will manage, right? So it is a marginally stable behavior if I choose k1 greater than 0. But I have to choose k1 greater than 0. You see this? How much greater than 0? When k1 equals g, that's when you will have them both at the origin. So k1 actually has to be greater than g to be on the j omega axis as two distinct complex conjugate poles on the j omega axis. So k1 has to be greater than g to make this into a marginally stable behavior. Still some question marks, right? So still marginally stable. We wanted this to be stable completely. What does that mean? That means that with proportional feedback, we are not able to completely stabilize the system. We are still getting marginally stable behavior. That means we are not responding fast enough. We are not changing A of t fast enough with respect to theta of t. So we need something else. What do we need? We need derivative feedback. So let's try to change acceleration depending on the derivative rate of change of theta of t, so that we can respond faster. So in time, if you differentiate in s, that would mean that you are multiplying by k2s, right? So this is our new feedback dynamics g of s. This is derivative feedback. Earlier it was proportional feedback. Now if you use this, go through the same process, closed loop transfer function, find out where the location of the poles are. You will see that there are two poles again that now depend on k2, the constant k2 here. Let's again do the same exercise. Put them onto the S-plane. When k2 equals 0, you still have one pole to be stable and one pole to be unstable. That's when k2 is 0. When you decrease k2, when k2 is less than 0, this guy moves right, more unstable. We don't want that. But this guy moves right as well. So that's good. That's okay, right? That's still moving towards right, so I don't like that. However, when you increase k2 greater than 0, then this guy moves left, that's good, towards stability. And this guy also moves left, is already stable, and it moves more towards stability. So the problem here is that if you increase k2, we might get some good news. The problem is that no matter how much you increase k2, this pole stops at the origin. It does not go over to the left half plane, which means the system is still unstable. So with proportional feedback, we didn't get stability. With derivative feedback, we didn't get stability. That means the only next step is to combine both of them. Let us see what happens if we use proportional plus derivative feedback. Let us try to see what happens then. So we have proportional feedback here, k1. You got acceleration that depends on theta of t directly, proportional feedback. And now we also have derivative feedback as well. So now the acceleration of the car depends on theta of t as well as the time derivative of theta of t. Two different constants now, k1 and k2. Go through the same process, find out, plug in a of s, plug in g of s in our closed loop transfer function, find out where the location of the poles are. It turns out that now the location of the poles depend on k1 and k2 both. Put them onto the S-plane. You will see that when k1 equals 0, the starting pole locations are k1 equals 0 and k2 is greater than 0. Right? When k1 equals 0, you start here and here, and k2 is greater than 0. You see what happens. When k2 is greater than 0, this pole moves left somewhere here, this pole moves left somewhere here, right? So we have actually first made k2 greater than 0. So we have initially moved both the poles to the left and then played with k1, right? So initially moved them to the left. So this moved here, this moved here, both moved left. So that's your initial starting point. Then you increase k1. Now when you increase k1 greater than 0, what happens? This pole is now able to cross over to the left half plane, becoming stable. This pole also is stable already. They are going to come together. They are going to break away and travel. One pole is going to go up and one pole is going to go down. Now, as long as they are in the left half plane, they are going to be stable. What is happening to the system behavior what happens to the system behavior if the poles are here and here? Let me draw blue. If the poles of the system are where it is blue, right, as it's going up and down, if they are at blue, is there damping there? So you see there is damping there, right? So zeta is between 0 and 1 there, right? Over here on the real axis, zeta could be 1 or greater than 1. So as you change the damping factor, you could have oscillations or you could not have oscillations in your system output. Questions here? Because I really want to get to the demonstration now. So by using proportional feedback plus derivative feedback, we were able to get stable behavior. Now, there is a demonstration that I cannot conduct. However, Professor Alan Oppenheim, who wrote our primary textbook, has a YouTube video through MIT courseware where he presents this same lecture for the inverted pendulum demonstration. So, and I find this, tying very well. So I thought I would just walk you guys through this. I hope that my volume is low. I'm not sure whether you guys will be able to see this or not, but you can clearly see the title of the lecture, the feedback example, the inverted pendulum. And okay, so this is not working out very well. The timestamp that I'm going to recommend is 29:33 onwards. That's where I am right now. I will get to your question, Boris, in just a minute. All right, so this is not working out very well. Okay, all right. So I hope you guys are able to see this YouTube video, YouTube inside a YouTube, right? So he has an inverted pendulum that is mounted on top of a cart, and there is a motor that is controlling the movement of that cart, so the A of t. I'm going to go forward here. So that's your inverted pendulum, right? So clearly, if he drops the inverted pendulum, then it's going to fall over. But because now we have A of t, it's measuring theta of t using proportional plus derivative feedback to adjust the acceleration of the cart, and it is going to be a stable system. So in fact, even if he changes x of t, pushes the inverted pendulum, the system is still able to keep it stable, right? So as long as theta of t is small, right? So that's an assumption that we have to make. As long as theta of t is small, the system is linear and everything works out. So as you can see, the cart is able to keep the pendulum upright. Things are moving fine. Now, in order to make things a little bit more fun, he is going to place a glass on top of the inverted pendulum. And so essentially he's playing around with the x of t, right? The external disturbance. So when he does that, the system is still able to maintain it stable and it's not toppling over. So even if he changed x of t, it was still stable and things are fine. In fact, to make it even more dramatic, he pours a liquid in the glass, still stable. And you see now, take a moment here. The liquid in the glass is not sloshing, right? Which means it's an overdamped case. The poles are still on the real axis. There's no oscillatory behavior. The damping is a good amount of damping is there. Right, the system is pretty stable now. The liquid I can see is not sloshing around. It's pretty stable. There are some. It goes to the there are some oscillations, but they come back down again, right? And I go a step further from here. He will in fact remove the glass and then place the entire pitcher full of water on top of the inverted pendulum here. And when he does that, the system is still able to balance this out. However, you see what starts happening is the liquid inside that starts giving oscillations into the system, right? So the liquid is sloshing around, which means that now zeta is between 0 and 1, there are oscillations. So to increase damping, he actually puts back that water that he had grabbed earlier on, increasing the damping factor, no oscillations, get back to the system stability. So I find this demonstration to be very very good, and it ties math and the real world very well, which is why I went through this. Um, and if things did not transition very well on your end with respect to that video, I would encourage you to at least take a look at that video from timestamp 2933. That's where that demonstration is. But apart from that, this entire lecture was inspired from Professor Oppenheim's lecture on YouTube through MIT courseware. Okay,